In this lecture, we start the study of the derivative and its many applications. We begin by considering a specific problem of finding the velocity of an object at some point in time. Then we discuss the graphical interpretation of the velocity in terms of tangent lines. We generalize our findings to other rates of change and define the derivative as instantaneous rate of change. Consider an object traveling in a straight line. Denote by s of t the position of the object at time t. That is, s of t is the directed distance of the object from the origin at time t. The function s of t that describes the motion is called the position function of the object. The average velocity of the object over a given time period is the change in position divided by the length of the time interval. For example, if a car travels 200 miles in 4 hours, its average velocity during this 4-hour period is 50 miles per hour. At any given moment, the car may be going faster or slower than the average. The question is how to compute the instantaneous velocity at a particular point in time t equals a. Unlike the average velocity, we cannot define instantaneous velocity as a ratio, because we would have to divide by the length of the time interval, which is 0. However, we can estimate the instantaneous velocity by computing the average velocity over a small time interval. The idea is the following. Average velocity over a very small time interval is very close to instantaneous velocity. Let's compute the average velocity over the time interval of length h starting from t equals a. Then the change in position equals s of a plus h minus s of a. So, average velocity over the interval from a to a plus h equals s of a plus h minus s of a divided by h. Suppose we compute the average velocities over the shorter and shorter time intervals. In other words, we let h approach 0. The instantaneous velocity at time t equals a is the limit of these average velocities. V of a equals the limit as h approaches 0 of s of a plus h minus s of a divided by h. Let's apply this formula to the following example. A stone is dropped from the height of 100 meters and falls to earth. What is the velocity of the stone after 1 second? Here we need to find the instantaneous velocity after 1 second. To do this, we need to know the formula for the position function of the stone. Such formula is believed to be discovered by the Italian scientist Galileo Galilei in the 16th century. According to the biography of Galileo, written by his pupil, the following experiment took place. Galileo had dropped balls of the same material but different masses from the Leaning Tower of Pisa to demonstrate that their time of descent was independent of their mass. It was contrary to the teaching of Aristotle that heavy objects fall faster than lighter ones. Galileo's experiments resulted in the following law. Distance traveled by a falling object is directly proportional to the square of the time it takes to fall. If the time is measured in seconds and the distance in meters, then the distance traveled after t seconds is s of t equals 4.9 t squared meters. Let's compute the velocity of the stone after 1 second. The velocity v at t equals 1 is given by the limit as h approaches 0 of the difference quotient s of 1 plus h minus s of 1 divided by h. Using Galileo's equation of motion, we rewrite this quotient as 4.9 times 1 plus h squared minus 4.9 times 1 squared over h. We can factor out the constant 4.9 from the numerator and thus from the limit by constant multiple law. And then we can multiply out 1 plus h squared. We get 4.9 times the limit as h tends to 0 of 1 plus 2h plus h squared minus 1 over h. 1 and negative 1 annihilate each other, which enables us to factor out h in the numerator. We have h times 2 plus h over h. We cancel common term h on top and bottom of our fraction. And get 4.9 times the limit as h approaches 0 of 2 plus h. We compute this limit by simply substituting 0 for h and obtain 4.9 times 2 equals 9.8 meters per second. Therefore, the velocity of the stone after 1 second is 9.8 meters per second. The idea that average velocity converges to instantaneous velocity as we shorten the intervals has a vivid interpretation in terms of secant lines. By definition, a secant line is a line through 2 points on a curve. Consider the graph of a position function s of t for an object traveling in a straight line. We draw a secant line through 2 points on the curve, which correspond to t equals a and t equals a plus h. Let's compute the slope of the secant line. The slope equals vertical change over horizontal change. Horizontal change is the difference between a plus h and a, which is h. Vertical change is the difference between the values of the function s at a plus h and a. Thus the slope of the secant line equals s of a plus h minus s of a over h. Notice that this is exactly the ratio we used to define the average velocity over the period from t equals a to t equals a plus h. Therefore, the average velocity is equal to the slope of the secant line. Let's see what happens as the time interval gets smaller. In other words, let's find the limit when the size of the interval h approaches 0. We see that as the interval shrinks to a single point, the secant lines rotate into a line that skims the curve at that point. This line is called the tangent line. The slope of the tangent line is the limit of the slopes of secant lines as the interval shrinks. Since this limit also defines the instantaneous velocity at time t equals a, we arrive at the following graphical interpretation. Instantaneous velocity at time t equals a is equal to the slope of the tangent line at the point on the graph of the position function corresponding to t equals a. We can now use the limit of the difference quotient to define the tangent line to any curve. The tangent line to the curve y equals f of x at the point P with coordinates a, f of a is the line through P with slope m equals the limit as h approaches 0 of the difference quotient f of a plus h minus f of a divided by h. As an example, Let's find an equation of the tangent line to the graph of f of x equals 2 over x at point with coordinates -2, -1. We know that the tangent line goes through the point -2, -1. So first we write the point-slope form of an equation of the line through the point -2, -1, where we denote its slope by m. We get y plus 1 equals m times x plus 2. It is left to find the slope m. According to the definition of the tangent line, its slope m equals the limit as h tends to 0 of f at -2 plus h minus f at -2 divided by h. Note that a here equals -2. We replace function f by 2 over x and obtain the limit as h tends to 0 of 2 over -2 plus h minus 1 divided by h. We multiply the numerator and the denominator by -2 plus h to get the limit as h tends to 0 of 2 minus 2 plus h divided by h times -2 plus h. 2 and -2 annihilate each other, which leaves us with h in the numerator. We cancel common factor h on top and bottom of the fraction and obtain the limit as h approaches 0 of 1 divided by -2 plus h. This limit is evaluated by substituting 0 for h, which gives -1/2. We replace m by -1/2 in the equation of the tangent line and get y plus 1 equals -1/2 times x plus 2. The last step is to rewrite this equation in the slope-intercept form. The answer is y equals -1/2 x minus 2. Velocity is only one of many examples of a rate of change. Our reasoning applies to any quantity y which depends on another quantity x. That is when y is a function of x. Say y equals f of x. If x changes from x1 to x2, then y changes from y1 equals f of x1 to y2 equals f of x2. The change in x, denoted by delta x, is the difference between the x values, x2 minus x1. The corresponding change in y, denoted by delta y, is the difference between the y values, y2 minus y1, which equals f of x2 minus f of x1. The average rate of change of y with respect to x over the interval from x1 to x2 is the difference quotient delta y over delta x equals f of x2 minus f of x1 over x2 minus x1. By analogy with velocity, we consider the average rate of change over smaller and smaller intervals by letting x2 approach x1, and therefore letting delta x approach 0. The instantaneous rate of change of y with respect to x at point x equals x1 is the limit of the average rates of change as delta x approaches 0, which is the limit as x2 approaches x1 of f of x2 minus f of x1 divided by x2 minus x1. The word instantaneous is often dropped. When we use the term rate of change, it is understood that the instantaneous rate is intended. Let's denote by h the change in x, x2 minus x1, and denote point x1 itself by a. Then x2 equals x1 plus h equals a plus h, and h approaches 0 as x2 approaches x1. Using this notation, we can rewrite the instantaneous rate of change as the limit as h approaches 0, f of a plus h minus f of a divided by h. We define the derivative of the function f of x at x equals a to be the instantaneous rate of change. Precisely, the derivative of a function f of x at x equals a is denoted by f prime of a and is defined by the limit as h approaches 0 of f of a plus h minus f of a divided by h. When the limit exists, we say that f is differentiable at a, otherwise f is not differentiable at a. An equivalent definition of the derivative is f prime of a equals the limit as x tends to a, f of x minus f of a divided by x minus a. It follows from our discussion that slope of the tangent line, instantaneous velocity, or any other rate of change are all different interpretations of the derivative. Let's use the definition of the derivative to find f prime of a for f of x equals square root of 3x plus 1. Then use the answer to find the equation of the tangent line at point 1, 2. The definition of the derivative states that f prime of a equals the limit as h tends to 0 of f of a plus h minus f of a divided by h. We replace the function f of x here by square root of 3x plus 1 to get the limit as h approaches 0 of the square root of 3 times a plus h plus 1 minus square root of 3a plus 1 divided by h. At this point, our goal is to compute this particular limit, and we will utilize the techniques of evaluating limits we learned so far. We try to substitute h equals 0 and obtain an indeterminate expression 0 over 0. The next step is to simplify and cancel. Since the numerator involves radicals, we multiply and divide by the conjugate. The conjugate of the numerator is square root of 3 times a plus h plus 1 plus square root of 3a plus 1. We leave the denominator as a product of h and the conjugate. In the numerator, we obtain the difference of squares, 3 times a plus h plus 1 minus 3a plus 1. We multiply out 3 in the first term and distribute minus in the second term of the numerator. We get 3a plus 3h plus 1 minus 3a minus 1 on top, and the bottom stays the same. (3a) and negative 3a annihilate each other, and so do 1 and negative 1. 3h is the only term left in the numerator. Now we can cancel the common factor h on top and bottom of the fraction. We end up with the limit as h approaches 0 of 3 divided by the square root of 3 times a plus h plus 1 plus square root of 3a plus 1. This limit can be evaluated by substituting h equals 0. Notice that setting h to be 0 makes the first radical equal to the second. We obtain 3 over 2 times square root of 3a plus 1. Therefore, the derivative f prime of a equals 3 over 2 times square root of 3a plus 1. Now we turn our attention to finding the equation of the tangent line at point 1, 2. We know that the slope of the tangent line at a point 1, 2 equals to the derivative of f at 1. We use the formula for f prime of a with a equals 1 and get the slope m to be 3 over 2 times square root of 3 times 1 plus 1 equals 3/4. Since we know the slope of the tangent line and the point on it, we write an equation of the tangent line in point-slope form. Y minus 2 equals 3/4 times x minus 1. The last step is to rewrite it in slope-intercept form. We obtain y equals 3/4 x plus 5/4. Before the end of our lecture, let's summarize the main points. The derivative of f of x at x equals a is denoted by f prime of a and is equal to the limit as h tends to 0, f of a plus h minus f of a over h. If the limit exists, we say that f is differentiable at a. The tangent line to the curve y equals f of x at point P with coordinates a, f of a, is the line through P with slope f prime of a. The equation of the tangent line in point-slope form is y minus f of a equals f prime of a times x minus a. The instantaneous velocity of an object traveling in a straight line is s prime of t, where s of t is the position of the object at time t. This is the end of our lecture.